I will just take 5 minutes to just recap on this fault resistance part, because there was a request about uh, some little bit lack of understanding or lack of clarity on this fault resistance. What are the fault resistances that are involved when a fault takes place? Only the resistance part. Impedance we all understand, it's the line part. But resistance is what is getting between two conductors for a face-to-face fault, and the conductor and the ground back to the source, and to the conductor, rather back to the source. This is the part. This is the fault resistance in a LG fault, in a ground fault. The ground fault is a little more complicated. I'm just repeating this one once again and then going to today's whole thing. So those of you who have participated in the last one will find this one a bit repetitive. But just let me repeat for the sake of some other people who might not have got the proper idea. So in a face-to-face fault, where this is a tower, this is the equivalent circuit of a tower and a bushing. These are sorry, let me do this pointer. Let me laser pointer. This is the equivalent of a tower carrying conductors. These are the this insulator strings, these two. And when a LL fault takes place, there is a conductor to conductor flashover. The flashover may be via, through air, which is denoted by this line over here, the distance between, and in that case, the distance between the two conductors, the face-to-face conductors, the highest distance between the face-to-face conductors becomes the cause of my arc resistance, which is denoted by R arc PP. And there might be a case which is very rare in this world when flying objects create a face-to-face fault. But there have been cases which happen. So suppose a tree branch during a storm or something like that, there are flying objects which create face-to-face fault also. So that is denoted by this R3. So these are the cases for LL faults. For a LL fault, the primary the primary resistance will be R arc PP, R arc face to face, arc resistance of face to face. Okay, now let me go to this LG fault. Actually, this was the page which was a little bit questioned. In a LG fault through an external object. Now, external object means suppose a tree comes very close to a conductor. Now, what is the path of the fault current? So here you see in this diagram, this is the tree, this is the representation of a tree. This is coming in very close vicinity with a conductor, and the arc is passing, and there's a flashover between the conductor and the tree. So the resistance involved is arc resistance between the conductor and the tree. Then the tree resistance, the charge passes to the ground via the resistance of the tree. This tree resistance can be quite high. It can be even 100 ohms. Hundreds of ohms also can be seen. But in general, 30 to 50 ohms will be okay. If we can cater that part, most of the faults will be taken care of. Most of the external object faults will be taken care of. So this is the tree resistance. The current path comes to the ground. Now it gets divided into the source part, rather the local end and the remote end. So let us say a 10,000 ampere fault current is flowing, 4,000 goes to the remote end, 6,000 comes to the local end. The local end, again, it has two methods of going. The easiest method, if the ground wire is well maintained and everything is okay with the ground wire, this current will rise up to the nearest towers. This tower maybe. Mostly from the nearest tower, it will rise up to the ground wire, then go through this ground wire path and reach the substation earth mat, and from there it will rise up again via the various neutral points. Now, this substation does not mean only the nearest substation. It can mean various other substations too. From the other substations, the current will get summed up via various lines and it come to this particular R phase via the other lines, which I have not shown over here. it was not possible to draw everything over here. So those currents, this Ig represents all those currents which are going to other substations maybe. So other substations currents get summed up in this R phase and R phase bus and comes back to the fault point like this. And this substation, the ground wire carries most of the current, and it returns back to the various substation arc points, transformer arc points mostly, and gets summed up over here. So whatever is the current, the fault current over here gets summed up in the line city, or the city, this line city of this particular conductor, and this is why the distance relay operates. The city is getting current, the voltage is dipping, and those parts are okay. So what are the resistances involved? The resistances involved are arc resistance, the tree resistance, and the power putting resistance. And this is our structure is the tower structure resistance, which is negligible, as I told in the last one also, mostly very low for metallic towers. This can be included in the tower putting itself. So this is why all these three resistances are involved. And the portion of this Ig, the ground current and the ground wire current, the impedances incurred by the fault current through the via the ground and the ground wire are taken care in the reach diagram by this K0 factor. We'll learn about it today. This one I had to leave it yesterday, last time. Okay, now this is the external object. There can be another, explain the, I cannot see the, okay, I'll try to explain. Now there is another type of LG fault, which is the insulation flashover. One was external object touching the conductor. Insulation flashover means you have a the most common source of insulation flashover is lightning strike on the ground wire. Now, whenever there is a lightning strike on the ground wire, this does not directly constitute to the fault. The lightning strike gets grounded through the R structure and the R tower, and the matter ends over there. So why does generally all lightning strikes do not create faults? Lightning strike create faults when what happens when a lightning strike? The tower gets elevated to a very high potential, and that creates a flashover between the conductor and the tower structure. Because the tower structure is at a very high potential, the conductor is relatively at the lower potential at that moment of time. This creates the conductor flashover between the conductor and the tower structure. This is the mechanism of this lightning faults. So really speaking, the lightning current is not seen over here. It is the flashover of this conductor and the tower structure that is creating the ground fault, but the source cause is the lightning. That is what I understood in this phenomenon. If I am wrong, okay, please correct me, but this is how I see the game over here. So whenever there is a, now come back to the insulation flashover part. Forget the lightning part. So the insulation flashover means the current is flowing from the conductor to the tower body to the ground wire and coming back to the substation arc mat, and like the previous example. Now what happens when the ground wire is cut over here? Then this tower footing and all these guys will come. It happens in our system, in our DVC system also, in any other system also. Lots of times it happens that there's a breakage in the ground wire. Then what happens? This current do not have the path to go through this. The lowest impedance path is cut over here. So then it goes down to the structure and tower and goes up to the next tower probably. Whichever is nearer or whichever is of a lower impedance, the ground may be of a lower impedance, the nearest tower and the and the next ground wire may be of the lower impedance. Whichever lower impedance path, then that it will take. So under those conditions, this tower footing resistance and this resistance will come into picture. So in insulation flashover also, there can be an arc. Arc is this path. This is the arc path. The conductor to the body. This is covered by the arc. The tower footing this part, and any structural resistance if it is there. So these are the things involved in the insulation flashover kind of fault. So the conclusion is, if we can to take care of the ground fault in our distance relay reach, we need to plan for worst possible condition would be the previous condition where all these guys are involved. R3, the object resistance, the tower footing, the arc resistance, all these three players are involved, with the this object resistance becoming the major player over here. Generally, tower footing is around 10 ohm, 20 ohm maybe. In very rocky hilly regions, it has been found to be higher on the higher side. Arc resistance is not that much. Generally, something around 10 ohm maximum. It should not go beyond it. Very rarely you find. Okay. So if we plan our resistance according to arc resistance plus tower resistance and the object resistance, we can take care of all the resistive faults possible. That is the lesson from here. Now this was already covered, this page was covered. So in a LG loop, maximum we should provide maximum coverage of fault resistance considering the object resistance, arc resistance, tower footing resistance, which we were talking about. In a LL loop, in a phase-to-phase loop, fault resistance, if any object resistance is there, and the arc resistance mainly. This will cover all the LL faults, and in LL loop we need to take care that we cannot increase the. If we have a load encroachment if we have a load encroachment feature in the relay, then we don't have such a problem. But if we don't have, then we have to check the possibility of load encroachment of load in the fault resistance coverage portion. Next, we go to these are two diagrams I found in the book of Ziegler, the Siemens. He was a Siemens engineer, 40 years with Siemens. I just added it up. This was also covered in the last session. See I just added it for clarity. I found the diagrams interesting, so I added. Increase of fault resistance due to impede effect. I was talking last time as the fault goes away from my relaying location, the impede factor starts increasing. The I2 starts increasing, and that is what exactly is being shown. The initial area will not have that much I2, but as the relay, as the fault moves towards the remote end and beyond, the increase of this the remote end fault, remote end impede would be increasing, let's say exponentially, if not exponentially, at least parabolically, it will start to increase. So that is what is showing. So the more it gets further, the fault resistance, apparent fault resistance seen by this relay will start to increase. And this diagram is also good. It is showing the load encroachment and the increase of the apparent resistance. Both are same, nothing different in it. Just this is a more complete diagram, so I also put this one up. This x-axis is one this how many times this RF is being multiplied. That is what this is showing. 6x, 5x, this one. This axis. Okay, the next diagram also, this is a good diagram I found, so I added it up. This is the diagram of the thing that we were talking in the last presentation, the pre-fault load flow, the influence of pre-fault load flow on fault resistance. So just a very small recap, whatever be the fault resistance does not move always horizontally. It moves vertically downward or vertically upward depending on the pre-fault load flow angle, pre-fault load flow. What is pre-fault load flow? It is based on the angle difference between U1, this sending end, and the receiving end. U1 might be leading, U1 might be lagging. If U1 is leading U2, then load flow will be from U1 to U2. If U1 is lagging U2, then from U2 to U1. So depending on that, the fault resistance will come down or go up as shown in this diagram. If it comes down, we have a greater problem because a zone 2 fault, suppose this is in a zone 2 region and there's a zone 1 boundary somewhere over here. So it might come into the zone 1 region. We have a greater problem. And this is a zone 1 fault getting converted into a zone 2, which is okay with a carrier. If the carrier scheme is in service, then little bit of under it is poses lesser problems. Without carrier, again this can become a problem. So this diagram I just felt like sharing, that's why I shared. Now we come to today's main topic. Main topic is there are a lot of other topics, but this is a very important thing, and I find it quite confusing. This one, the zero sequence compensation for ground faults. Now, current in space fault loop depends on Z1 and Z2 of fault. Matlab this Z1 Z2 is not zone 1 zone 2. This is positive sequence impedance and negative sequence impedance of the fault loop, which are same for a transmission line. In a transmission line, as it is a non-rotating thing, the positive sequence and the negative sequence impedance of the transmission line is the same. Since the majority of the fault passes through the transmission line, so the Z1 and Z2 of the fault loop remains almost the same in a phase fault, phase-to-phase fault. But the current in earth fault loops, therein all the complication starts. Depends on Z0. It depends on Z1, Z2, of course. It also depends on Z0. The zero sequence network comes into picture. Now, zero sequence of a transmission line is different from Z1 and Z2. When you do distance area calculation, you will find that the manufacturer gives two values. One is the positive sequence value and one is the zero sequence value of the conductor. The zero sequence value is almost 3 times the positive sequence value, approximately 2.73 times. And again, one can also say that the zero sequence network is dependent on ordering locations with respect to relay, number of ordering points, methods of ordering, presence of star delta transformers, whether the current, this zero sequence current will pass through this point through the relaying location or not, that depends on the presence of star delta transformers, ordering systems and everything else. So a little bit things are involved in the zero sequence network. Okay, now why do we need this compensation? The mathematical reason is clear. You will find it, this equation can be explained easily. But the main source of the problem, let me go to the next page. The source of the problem is that, see, this return path, this one I know. There's a fault in A phase in this line. This is the equivalent circuit. This is of the source. This is the relay location. This is the fault current. This is the equivalence of the transmission line, which is having a fault. And this is the equivalent of the return path of the earth fault current. Now, the return path of the earth fault current consists of the ground wires, maybe the ground itself. We don't really know the impedance of this portion. We are in dark about this one. The return path impedance we don't know. So how are you going to catch this fault? And how are you going to be sure that this fault is kept or this fault is calculated properly? The distance to this fault or the impedance to this fault is calculated properly without knowing the return path impedance. Therein this mathematical logic of sequence component comes over here. Now, what we need to do is, we do not need, okay, this is the sequence network of a fault on one transmission line in a parallel line system. The reason why I am showing it in a parallel line system will be understood just now. I could have shown it in a single line, one line only. This line need not be shown. Now, over here in a parallel line, there is a fault at m percentage. The acronyms are almost clear. This is a line 1 positive sequence impedance. This is negative sequence of line 1. This is zero sequence of line 1. This is 1 minus m. From the other side, it is 1 minus m percentage. From this side is m percentage. This is the source impedance, source voltage. This is source impedance local, source impedance remote. This is the basic acronym. Source impedance positive sequence, negative sequence, zero sequence. And it gets connected like this. If there is a fault resistance, then fault resistance will come in this path, this path. Here the fault resistance will come into picture. And then if there is a fault resistance, then this cross will be after the fault resistance, because the cross represents the point of fault. So then this X mark will be after, including the fault resistance, which will be common to both these parts, because the fault resistance current is being fed, the current in the fault path is being fed both by the local end as well as the remote end. So the resistance will be over here and the cross point will be somewhere over here. I did not show it because I did not want to complicate this diagram further. As it is, it looks little complicated. Okay, so with this one, okay, so there are two methods. What I really need, I need the voltage at this point and the current at this point. But and I divide it, the VA by IA. If I do, I will really not get what I want. What I am doing with this equation is that I am actually measuring the voltage difference between the fault point and this relaying point. That is my idea. And if I have a fault resistance, that fault resistance will also come into this loop, this equation. So V1 does not represent over here the actual voltage with respect to the zero potential path. V1 over here, what I have drawn, represents the voltage from this to this, the difference of voltage from this to this. Okay, V2 is also the same and V0 is also the same. Now, how does this thing help? This thing helps that I will not take into consideration all my source impedance and the impedance, all this voltage of the source and all this. This area I can eliminate, my unknown area. This is my unknown area. I don't know the source impedance very well. But I am very sure about the impedance between the fault point and my relaying point. That is somewhat, I know that because it is a transmission line, impedance is proportional to length, all these things I know. Now come over here. So I can write the voltage at this relaying point is the sum total of the voltage, between this point and this point and this point. Obviously, we can say that because in a sequence network, if I add V1 plus V2 plus V0, I am going to get VA. Okay, now what is V1 plus V2 plus V0? With respect to this fault point, we are doing everything, not on an absolute scale. It will be I1 Z1, Z1 represents this one. I2 Z2, I2 represents the negative sequence current through the relaying location multiplied by the negative sequence impedance between the fault point and the relaying point. This is the meaning of this equation. And similarly I0. Now after this, what I do? I have Z1 equal to Z2 I can write, because in a transmission line this one equal to this one, these two impedances are the same, we know. So this Z2 I replace by Z1. I have skipped a little step over here, and it can be written like this. So Z1 I take common, I take I1 plus I2 plus I0 I add, and this I0 Z0 will remain, and this additional term I0 Z1 I subtract again. After that I get Z1 into, this one represents IA. What is IA? The current through the relaying location. The current through the relaying location is the sum total of the sequence currents of sequence current, positive sequence current, negative sequence current and zero sequence current, at least in A phase. That is why the fault has been taken in A phase, mathematically. Now just understand one thing, I have not written over here I1 equal to I2 equal to I0 and this as 3I0. I have written it, this one as phase current, because at this point I1 is not, I1, I2 and I0 may not be equal, may be equal, may not be equal. If I1, I2, I0 are equal for a ground fault, this is applicable only at this point X, at the fault location only, not at any other points of the network. So I have not converted this into 3I0. I have written this one as IA, and this is the method. This is the treatment found in all the books. You will find it written like this only. So if I have this IA, then this one I am this one Z0 minus Z1 into I0 I am having. So I am into I0. So what I am doing, I am dividing it by 3Z1 and multiplying it by 3I0 and taking Z1 common. So that this thing remains. This is a mathematical thing, you can understand it very well. Easy thing. After this, the manipulation is done with Z1 into IA. IA remains like this, and this one I term as K0, the residual compensation factor. Z0 minus Z1 by 3Z1, which is popularly known, multiplied by 3I0. Over there I can write 3I0 because I have been using 3I0 right from the beginning. But this one, this is the phase current. This is not equal to 3I0 all the time. This is what I want to impress. Where K0 is a constant. As Z1 means this one, MZ1 underscore L1. This is the Z1 we are looking for. This is equal to this voltage divided by this current. Simple manipulation, here, see the side change. So IA plus K0 into 3I0. Conclusion. The relay can measure Z1 independent of impedance and urging arrangements and everything else if a proportion of residual current, this is called a residual current, this 3I0 which will flow through this point is multiplied by 3 and added up to the phase current, added up to all the summation of these three currents in this network I'm talking about. And in that way, if a proportion of residual current is added to the phase current IA, then the relay can measure the proper impedance when a ground fault occurs on a transmission line. The proper impedance means the impedance between the fault point and the relaying point. Now next one, this is again the same thing, a little repetition only. We calibrate the distance relay effect of K0 on loop impedance. Now we come to an important concept called loop and par phase and par loop. That is why I have made this one. Now we calibrate the distance relay on a par phase basis based on positive sequence impedance of the transmission line. The distance relay reach diagram which we draw is based on the positive sequence impedance of the transmission line. But during earth fault, the ground return impedance needs to be included in the relay characteristic curve. This is done by expanding the Z1, the known, expanding the the positive sequence reach by a known factor K0. Thus, Z1 positive sequence reach in plus K0 factor multiplied by positive sequence reach in a complex plane gives the expanded reach characteristic which operates in LG fault loops. The Z0 of the transmission line should be preferably measured and not based on manufactured theoretical calculations. These theoretical calculations are based on the tower design and tower distances and all those. So preferably it should be measured. If not, okay, go on using the manufacturer given Z0 values. In cases of doubts where you are finding okay, my whatever distance the relay is showing during ground faults, it is not as per the real fault location, and my settings are all correct, my K0 calculation is correct, then measure the K0 with a test kit. There are methods to measure. Okay, now so this is how this expansion takes place. Effect of K0 on loop impedance, expansion of perfect sequence impedance loop. This is what I calibrate the relay to measure, but this is what the relay actually measures. Z1 is multiplied by K0 into Z1 and an increased loop is created. Increased circle or quad characteristic is created as shown in the next slide. This will give a very clear idea what happens. This is what we calibrate the relay in a Mo characteristic, and this is the loop characteristic. This is multiplied by K0. This is Z1 into K0. Suppose my operating point is the relay is the I have set the relay to operate at P2 for phase faults as well as ground faults. But as we have given a K0 factor, the relay actually sees up to this P2L. This is a very good diagram I found in one of the Doble papers. This is what we set the relay, the inner characteristic. This is what we set the relay, and this is what the relay actually responds to, the bigger one characteristic. So this is the positive sequence impedance of the line. This portion takes care of the return path of the fault point and the source. This part takes care of the loop resistive part of the fault. Okay, this is what this is. Okay, now we have one particular important, very important thing: the understanding of par phase and par loop. Now in today's world, this is more important because there are relays which define X in par phase and R in par loop. And for the utility of the user, it has become more user friendly. Today's relays are more user friendly. So this R axis, the resistive axis, is very useful when we define in par loop basis, and the X axis is useful. It is more user friendly when we define on a par phase basis. So I have examples of relays where par phase are also there, par loop are also there. I'll be showing just now. Anyway, what I mean to say over here is, in older generation relays, all RNX were entered on par phase basis as it was the language relay understands directly. Relay understands par phase basis. Relay will not understand par loop basis. I can enter the setting in par loop basis, but relay will recalculate the whole thing based on par phase basis. Okay, this is a help that the relay manufacturer has given to the users. In a loop equation, in a LL loop equation, in a phase-to-phase loop equation, I am skipping this, not skipping. Okay, let me cover, otherwise what am I doing? This is the phase-to-phase loop. Phase-to-phase loop takes place between what is the equation defining phase-to-phase loop? UL1 minus UL2, the phasor difference of these two voltages, divided by the phasor difference of these two currents. That is how this impedance loop is measured. So in this impedance loop, you can see that 2 times the line impedance is coming and 1 time the fault impedance is coming. So on a par phase basis, this RFPP, the resistance to fault on a phase-to-phase loop, RFPP, gets divided by 2. And this is a diagram in the ABB RL670 relay. You enter the setting in par loop basis, but the relay reach diagram will recalculate it by itself on a par phase basis, and it is shown that when this R becomes ohms per phase, this becomes divided by 2. Okay, so this mathematics of this is given over here. I hope I was able to explain, because 2 times of this impedance is being taken, 2 times the line impedance is coming into picture. The phase-to-phase loop impedance gets divided by 2 when it is done in a when the relay reads it ultimately in a reach diagram. Matlab, the main thing is that when you test the relay, then this loop impedance has to be divided by 2 to draw the par phase diagram. Otherwise, your relay testing will go wrong. That is what is shown by this. Since loop equation involves IL1 minus IL2, the phasor difference in the phase currents, and UL1 minus UL2, the phasor difference between the phase voltages, we calibrate the X reach, and we calibrate the x reach with x1 and not 2x1, we need to use RFPP divided by 2 to match the per phase characteristic. So in a per phase, the loop impedance of a phase to phase gets divided by 2 to keep matters okay. Now this is the Areva Areva reach diagram. In Areva reach diagram, this R1H, we suppose we need to enter 30 ohm in RFPP in the R1PH. Phase to phase loop coverage, I need 30 ohms. So I will have to enter 30 ohms in R1PH in the relay, because the resistive reach in the Areva relay is set on a per loop basis, not on the per phase basis. In a Areva relay, the reactive reach, the X reach is set on a per phase basis, and the resistive reach is set on a per loop basis. It is not written directly, I think, in the manual, but this diagram is from the manual itself. So when I enter 30 ohm, the relay actually sees a 15 ohm per phase resistance. That is what I wanted to impress. Okay, so if I need the important point is the red point. If I need a 30 ohm loop coverage, if I need a arc resistance plus free resistance, object resistance coverage of 30 ohm, I need to enter 30 ohm in this R1 phase directly. I should not divide it by 2 and make it 15 ohm. Okay, but see the next relay. This is okay. Let me go to this slide and then I'll come back. See, this is a Siemens relay. Siemens relay, if I need a arc coverage of 8 ohm, I will have to set the relay at 4 ohm. Otherwise, it will go wrong. Because the phase to phase RZ1 phase to phase is in a per phase basis. Again, this is not directly mentioned in the reach diagram, but only mentioned in the setting hint. In the setting hint, this is taken from the setting hint. Okay, so this is the what to say. This is the setting page, option page diagram from Siemens. Those who are familiar with the 7SA manual, they will find this familiar. Address, the terms. So over here, this particular setting, the R phase to phase is on a per phase basis, whereas the R phase to R is on a per loop basis. Guess what, I'm coming back. Okay, now let me again go back to phase to earth, and at the end of both you will understand it better. Okay, this is the per phase and per loop for phase to earth faults. Now over here what happens, the difference, the equation on which this phase to earth loop is based is UL1, the phase to earth voltage, the voltage of the faulted phase with respect to the neutral, and divided by the current. Now the current is the same in this whole loop. So this is over here, this RFPE need not be divided. This RFPE is the loop impedance, not the per phase impedance. In order to get the per phase impedance, we will have to convert it. We will have to divide it by 1 plus K0 factor. Then only you will get. And the mathematics is given over here. So I'm just reading out. These things are little bit difficult to explain in presentations. If I could have written it in front of you in the board and shown, it would have been easier to understand. But anyway, I hope I'll be able to explain. If not, reread this once more, you will get it. Using Kirchhoff's voltage law, UL1 minus IL1 into Z1. Z1 is this one. Minus RFPP into IL1. RFPE into IL1. This part. Minus IN into K0 into Z1. K0 into Z1 is this part. This impedance, the return impedance. And IN is the neutral current as shown earlier, as discussed earlier. This equal to 0. Now, if we rearrange it, you will find that UL1 divided by IL1, which is how we calibrate the relay, is equal to Z1 into 1 plus K0 plus RFP. Now, Z1 into 1 plus K0 is already done by the relay as explained earlier. This is the relay expands its positive sequence reach. The relay expands its positive sequence reach by 1 plus K0 factor in order to, matlab Z1 plus K0 into Z1, the relay already done. The left part is the RFPE. So in a loop diagram, okay, sorry. In a loop diagram, so RFP, the resistance of the earth fault loop, means the arc plus tower footing plus object resistance. This has to be divided by 1 plus K0 in order to go to the per phase mode. See, this is the reach diagram of RL670 relay. It is written ohms per loop. Over here also it is written ohms per loop. The reason I am explaining only this resistive ohms per loop, I am not explaining this one. The reason this one comes ohms per loop is that in RL670 relay there is no concept of K0. You have Z1, Z0 directly mentioned. So you mention the K0 into Z1, this part is taken directly. Matlab, I mention it to the relay directly. I do not mention it in a K0 factor mode. Okay. Okay. Conclusion. Since the loop equation involves Z1 into 1 plus K0, but we calibrate the relay using Z1, we need to use RFP divided by 1 plus K0 to match the per phase characteristic in resistive axis. Let us see an example, you will get it. See, this is the resistive, the per phase zone diagram of an Areva relay. If we need a RFPE coverage, if we need a tree plus arc plus tower footing of 50 ohm, we enter directly 50 ohm in the R1G setting, and the relay divides it by 1 plus KZ, the compensation factor, internally to create the per phase diagram. You don't have to do it anything outside the relay. But there are relays where you have to do this thing outside. The setting engineer has to incorporate this thing in his setting in order to get the same 50 ohm coverage. Let us go beyond this. This is a Siemens relay. In Siemens relay also is like Areva relay. The phase to phase is on a per phase basis. The phase to earth impedance, the phase to earth resistance is on a per loop basis. You can see from here RE1 primary equal to RR plus R tower. If I want a 18 ohm coverage, I have to enter 18 ohm only. This NCT by NBT is the secondary part. I have to enter 18 ohm. But if I need a coverage of 8 ohm in the phase to phase loop, I have to enter 4 ohm. Then only it will work properly. This is a GE D60 relay. Over here, all is phase to phase. There's no loop concept over here. Everything is phase. So in a 21P function, if we need a resistive coverage of 30 ohm, we have to enter 15 ohm. The right blinder in a phase to phase function, the 21P function has to be divided by 2 and entered. And in a 21G, if we need a 50 ohm coverage, we have to divide it by 1 plus K0 and then enter. This is the resistive, RE loop or LG loop. This is the LL loop, this is the LG loop diagram. So both diagrams look the same. You cannot understand it by seeing the diagram. You have to perform tests and then only understand, okay, this is this. This has been tested experimentally and also agreed by GE engineers. We actually questioned GE engineers about this and they sent us a reply on this. Okay, so I hope I was able to clarify this par phase and par loop, which is sometimes misunderstood when we test relays and all, and our tests go wrong, and we find okay, it's not happening, what is going wrong. Okay, now we come to distance starter setting. These are certain miscellaneous settings. Nowadays, starter reaches are not used as such. Most of the relays do not have starters. This was the previous concept. Previous concept was that, I mean, 2000 to 2000, let's say 90s to 2004, 5, 6, 7, 8 relays, we had starters. And after the starter used to start, then only the zone will start. So first you had to have some starter things. So starter could be of three types. I'm talking about this one later. Starter could be of three types: under impedance starter, overcurrent starter, and under voltage starter. Starters are important because certain times it starts the distance zone timers. Sometimes it starts carrier protection timers. It can be useful for triggering DR in the system or system disturbances. Starter reaches are larger, so if I have enough number of DR in the relay, I can use the starter reaches to trigger my DR to understand the nature of disturbances which are occurring far away from this particular relaying location. I can see what is the effect of tire 2 fault maybe at a tire 0 at my location. 3 substations beyond a fault occurs, my relay picks up a DR based on the starter settings. Okay. But this is not a part of the tripping mechanism. Understand this. Okay. Now it is wise to use relay default setting, as different manufacturers use different starter algorithms. So better not use our own brains on it. The certain basic guidelines can be followed. The basic guidelines are that but remember one thing, if there is a starter zone, the starter zone has to start before the zone will come into picture. So if we have mistakes, if we have some mistake, like in one case study I discussed in the earlier session, there the earth current of the starter zone was too high, and that is why the zone did not come. So it is important. ऐसा नहीं है कि एकदम फालतू चीज है. Can come into picture if it is present. So if the ground fault start current should be greater than the maximum unbalanced current in the line, but lower than the lowest possible fault current. So it should be greater than the normal unbalance, but lower than the lowest possible earth fault current. The phase fault starter should be above the normal load current, obviously, otherwise it will always have a start. And if we have the starter reach, if it is the under impedance starting, then it has to be greater than the highest active zone. Suppose my zone 3 or zone whatever is active. In Areva nowadays you have so many zones, 5, 6 zones. Okay, Areva does not have a starter directly, it has some default starters. In the Areva 442 I'm talking about. 21G, 21P under impedance starting, then what we'll have to do, we have to keep the starter zone greater than the highest active zone. And if it is the under voltage starting, then we have to keep it lower than the lowest system voltage envisaged. Maybe 80%, 70%. Matlab, if the system voltage falls below 70%, then it is a fault. Otherwise, it is not a fault. So 70, 80% would be okay. So this is one example of a starter zone. This is the distance zone, the under wala, smaller one, and this is the starter zone. The starter zone is also restricted by the load encroachment characteristic, as shown over here. This is the example of a Siemens voltage current starter. You see, as the current increases, this is a short circuit area where the voltage is lower and the current is more. This area, and this is the load area. The voltage is more and the current is lesser. This is the load area. The voltage, more voltage, lesser current. Yes, this is a load area. So we draw the thing like this. We have four settings: I phase greater, phase double greater, U greater, double greater, and we have a plan. Okay, this is my differentiate the normal load area and the short circuit area, and this is how the relay starts. After that, the starter does not mean the relay will trip. It is just the starting of the distance functionality. Distance function start, pick up, but not the zone pickup. There's a difference between zone and starter. Some other settings, directional blinders. Normally, directional blinder. I don't have a picture. I can. Okay, let me have this picture. So this is the directional blinder. We all know that distance relay is directional. So distance relay, this is the directionality, the forward zone. This is the forward zone. This is the reverse zone. These are all reverse. This is the load area. This is the starter characteristic as shown over here. In Siemens relay, this is an example of a Siemens relay, 7SA relay. In Siemens relay, we do not directly have start. We have starter under impedance. We don't directly have starters. This is a zone 5 which we can use for triggering DRs and starters and things like that. So this is what I meant by starter over here. Actually, this is a distance zone. This can be used for tripping also. Okay, so directional blinders is this one, which demarcates the forward and the reverse zone. Okay, now one thing, this part is a no forward, no reverse part. If I have a 45-degree line and a 135-degree line, matlab this is 35 and 135 and this is minus 45. If I have a directional like this, then there is a clear demarcation between forward and reverse. But over here, I restrict my forward zone to some, let's say, 25-degree in the second quadrant and 25-degree in the fourth quadrant. In the first quadrant, I can restrict it like that so that there are no maloperations of the relay. If the fault somehow falls between this part, the relay will not operate. Now, going back to the previous slide, this is a directional blinder. Most times preset at plus 45 to 145. Sorry, this will be minus 45. Minus 45 to plus 135 or lesser. It has to include the full first quadrant, that is a must, and some part of second and fourth quadrant. Now, if somebody questions, okay, sir, why does a fault come in second quadrant? There can be faults which come in second quadrant, maybe some, and there can be faults which can come in fourth quadrant. Maybe some capacitor is involved in the fault, some capacitive impedance gets involved, then the fault can come in the fourth quadrant. Second quadrant, in the case of inter-circuit faults where one circuit touches another, the fault can come in second quadrant. And if you want my relay to trip in those sort of faults, I have to include the directional blinders more than the first quadrant itself, so that all the faults are checked. Memory voltage validity. This is a newer relay concept, the concept of memory voltage. Nowadays we have memory voltage used to understand directionality. Now understand one thing, memory voltage is not used to understand the impedance of the fault, otherwise it will always have 100% impedance. If I use memory voltage, I have to use the faulted voltage. Memory voltage is used to check whether the fault is in forward or reverse, and generally some validity setting, the time validity, how long memory voltage will remain active. That is what this setting means. Generally 10 seconds or whatever the relay default is given is sufficient. There's a concept of zone overlap, whether higher zones encompass lower zone or they remain separate entities. Generally we have overlapping preferable. This is only applicable. This is applicable for some relays. Typically, Areva relay have this thing. Whether a zone 2 fault, a zone 1 fault will appear as a zone 2 pickup also, or will it appear as a zone 1 pickup only and zone 2 will never operate on it. So overlapping is preferable. If I have a overlap mode enabled, that means my zone 1 fault is treated as a zone 2 pickup also, zone 3 pickup also, and any other higher zone pickup also. That if my zone 1 contact or the Zone 1 tripping relay fails to function, while Zone 2 tripping relay will function and clear the fault. That is the advantage of having overlapping added. There's a CVT transient detection logic. Now this is a totally different idea. What is this? In CVT, what happens if we have a line CVT, and probably for active CVT, this is when the CVT carries active components. This is a problem. If it is a passive CVT, then it's not that much of a problem. Nowadays, most of the CVTs are passive CVTs, so active CVTs have been done away with mostly. So this is not that important. But if we have a CVT transient malfunctioning the relay zone 1 because the transients are activated mostly for the first one and a half cycle, maybe 20-30 milliseconds. So what this logic does is, if it understands that there's a particular situation where the CVT transients are taking place, the zone 1 is delayed by a settable time to avoid zone 1 overreach. What happens in a CVT transient? This is a big topic by itself. A zone 2 fault gets seen in zone 1. The voltage is seen lesser. So the current is there, the voltage is lesser, so the zone 2 fault seen in zone 1 and the relay can overtrip. So if we delay the zone 1 by around 20-30 milliseconds, this transient will go away and the relay will perform perfectly. When this is activated, I wrote it somewhere. We wrote it. I think I wrote it when I will take up that SIR issue. This is activated for high SIR lines where the source impedance is very high and the line impedance is relatively less. There, this CVT transients get activated very much, and there this is needed. Otherwise, it is not needed. In most of our cases, in today's all interconnected grid, the source impedance is not that high. So mostly this is unused setting. Z1 tilt angle, we discussed earlier in the earlier class. We discussed that most of the relays give option of tilting the zone 1 boundary to compensate for reach and underreach due to high pre-fault loading. The typical value will be 3 to 5 degree for zone 1. Generally useful when pre-fault load flow angle is greater than 15 degree. So this one has to be seen as per, user, experience. Experience will tell whether you will give a tilt angle or not. No hard and fast rule for it. Normally in longer lines, we will need it because over there the chances of this overreach underreach will be higher, because the pre-fault load angle for a longer line, suppose there's a 20-kilometer line and there's a 100-kilometer line. The pre-fault load angle difference between in a 200-kilometer line will be more than 15 degree probably, but for a 20-kilometer line it will never be more than that. For longer lines with a very high pre-fault loading, this thing becomes important. Zone timer start. There's an option between, most relays do not give any option, but there are relays which gives option that whether the distance relay timing will be from zone pickup or from distance pickup or zone pickup. What it means. This is important. There was a case, I remember, where this was a culprit. Now, what is meant by timer pickup from distance pickup? This means that whenever I have a fault in zone 1, my zone 2, zone 3 timer is also starting. I have a distance pickup also, zone pickup. My zone 2, zone 3 timer is also starting. Suppose I have a zone 1 pickup, zone 2, zone 3 timer is also starting. By the meaning of zone pickup, I mean if I have a fault transiting into zone 2, then only my zone 2 timer will start. So I have a fault coming from zone 3 to zone 2 to zone 1. Okay. Then what will happen? If I have a fault transiting from zone 2 to zone 1, my zone 1, I've forgotten what it actually means. No, I'm not forgotten, a little confused. Timer start. Just let me get back a little bit. Sorry for the little glitch. Let me think. What happens is that, okay, this means that if I have a zone 1 start, then only my zone 1 timer will pick up. If I have a zone 2 start, my zone 2 timer will pick up. If I have a zone 3 start, only my zone 3 timer will pick up. My other timers will not pick up. Okay. So what happens in this case, if I have a fault transiting from zone 2 to zone 1, my zone, or rather zone 3 to zone 2, my zone 3 timer has picked up, but my zone 2 timer has not picked up. So when it transits, it will again time for the zone 2 time before tripping. So that will uselessly waste some tripping time because the fault has already started. So it is better to use the zone timer starting from a general distance pickup or any zone pickup. Even if a higher zone picks up, the zone timer will start. That is a better option, and that is the modern philosophy used in default in most of the relays. All the distance timers, zone 1 timer, zone 2 timer, zone 3 timer, in Areva it is shown as T1, T2, T3 for people who are using Areva relays. All these timers start at the same time. ऐसा नहीं है कि zone T2 starts later. It is after T2 ends, then zone 2 will trip. After T3 ends, then zone 3 will trip. The utility of this is that in a transiting fault, in a fault which transits from a higher zone to a lower zone, the lower zone will not wait for another timing of itself to trip. It will trip immediately. So we have a faster clearance maybe. Okay. Now this is about zone timer. This is the zone time diagram in totality. Now this is what I was talking about, effect of source impedance ratio. Now source impedance ratio is the ratio of the source impedance divided by the line impedance. And IEEE C37.113 guide for protective relay applications to transmission line classifies line length based on SIR. It does not classify line length based on length. Typically, line length should not be classified based on length of the line. It should be classified based on the source impedance ratio. If we have even a 10-20 kilometer line having a source impedance ratio less than 5, it can be classified as a long line. On the medium line it is this, and for a short line this is the cause of concern for us. This is the place where line differential comes into place. The classification is based on this ratio being greater than 4, so that the source impedance is very high and the line impedance is very low. Why is it a problem? If the source impedance acts as a voltage divider, the voltage received by the relay during a fault. This is a short circuit. Let's see the diagram on the right. The short circuit, this is the voltage, let's say this is a V fault which is 0. This is the V relay and this is the V source. This is the profile of the voltage will fall from the source to the fault where the relay comes somewhere in between. If I have a very high source impedance, what happens is that even if I have a 100% source voltage, the voltage received by the relay is very less. It is only 20%. But if I have a lesser source impedance, the voltage received by the relay is more. It is 67% maybe for a SIR 0.5. It is shown in this diagram. What happens? This is also not a problem. The problem is errors, the CTPT, CVT errors get magnified when the relay at the voltage terminal decreases, during a fault, and that causes the maloperation of relay. For a 67% voltage, if I have an error of 1%, it is not a problem. But for a 20% relay, if I let's say sorry, not the percent. Let's say I have an error of 1 volt in the secondary level. When the voltage received by relay is is originally lesser due to the high source impedance, then I have a tendency of my relay to malfunction or maloperate. That is why for a SIR greater than 4, zone 1 reach, people have to be cautious. This is not something very strict or something. Okay, if I have a SIR more than 4, I cannot use distance relay. Not like that. This is just a boundary where the setting engineer has to be cautious using zone 1 reach. Maybe reduce it to 65% from 80% to avoid overreach or go for line differential. Reference 14 provides details of SIR calculation methods. You can see the references given at the end of the presentation and you will find it. Okay. So now in my experience, I have one experience with one particular line which is quite a short line, where the SIR was not more than 4, it was around 2.5, and that line always used to trip in zone 1 for a remote bus fault. So we reduced the zone 1 reach to 65%, and after that nothing happens. For a bus fault, zone 2 comes, zone 1 doesn't come. So I have seen this thing happening, and there was no explanation that could be given, because under all other conditions the relay is measuring perfectly okay. So only due to that source impedance ratio this thing was happening. My zone 2 fault was becoming zone 1 always, every time it happened. Okay, so this is it. The next topic is loop equation. Loop equation is not the actual topic. The actual topic is delta equation. I will not talk very much about delta equation because that's a total algorithm difference. So it's a modern concept of understanding faults. The traditional the equations are always ZL1 L2 equal to the difference of voltage by difference of current. The traditional phase to earth impedance is the phase to our neutral voltage divided by the phase current plus the K0 into the neutral current. So these 6 equations are being evaluated in a distance relay continuously, and the lowest found impedance is compared with the set impedance, and if it becomes lesser, the relay trips. Okay. This line I can come back later after this, after the next slide, or I can. Okay, this is the only option for low fault current. If the pre-fault current cannot be modeled, the meaning will be clear in the next slide. So in modern relays, what they have done to minimize time, because over here a lot of things are involved. The direction is involved, or some phasor calculations and all these things are involved. So these things takes around 20 milliseconds by any relay to process. Below 20 milliseconds, it is impossible for any relay to process so much amount of information. But what the modern the delta equation says, you do not wait for all those calculations to happen to understand a fault. You understand a fault using the difference of voltage and the difference of current. If the difference of voltage is 10%, more than 10%, and the difference of current is more than 20%, all are instantaneous values. Okay, so you do not have the phase angle in picture. Instantaneous values contains the phase angle inbuilt. A cos omega t, that cos omega t is inbuilt in A instantaneous. Okay, so it operates on instantaneous values. That is why they are very fast. Within 3, 4, 5 milliseconds, it can predict there is a fault or not. And since we are talking about delta values, the DC components and those things are eliminated. We are talking about differential values over here. Differential voltage, differential current. That is how the modern relays are becoming sub-cycle. We are talking about sub-cycle relays. 5 millisecond, 10 millisecond. I think the modern, some relays are there which are promising to give its shift signal within 11 milliseconds. So those are all based on these things. Fault start if delta V or delta I is valid for 3 consecutive samples. Now you increase the sampling rate to get the fault faster. Faulty phase selection, I will not explain the internals of this. This is the Areva relay example I have taken, but what I only mean over here is that you can have phase selection, you can have directional decision based on 5 consecutive samples. Directional decisions are based on power, whether delta V into delta A is negative, positive, it gives this forward reversing. And the LG fault or a LL fault, that also depends on power. Okay, it's a multi-phase fault. If you read through this, you will understand. If the power of Cn is greater, is the greatest, it is a Cn fault, subject to other conditions over here. No fault in A and B, A to B, that also has to be seen. Okay, so main of the advantage is the speed of operation as processing is done on instantaneous values. Principle of fault detection is its comparison with pre-fault states. Therefore, fault detection is in comparison with pre-fault states. What does it mean? Everything can be done with this? No. The conventional algorithms also run in parallel, but the fault start and those things are done with this. If there is no discrepancy, if the previous values and the pre-fault values are all present, then this algorithm takes over and gives its decision fast. If there is lesser current or the current is, there are algorithms, I cannot explain everything over here. Then this algorithm, the traditional algorithm which is always running in parallel, comes into picture and takes the tripping decision. So we are combining the advantage of both the faster tripping as well as the little bit delayed to make it security. Speed and security are being amalgamated using both these parallel algorithms together. This much only I want to share. This is a real, I mean, fully complicated topic. If you have to understand delta equations, these equations itself are very much what to say, intimidating. If you really go and see the Areva relay, the first part of the Areva P442 manual, 44X manual, you will find these equations over there, the delta equations. Okay, this is how it does it. This is the pre-fault. No, sorry. It's basically the measured current and the predicted current. And the predicted current is the what should have happened without a fault. And this is the measured current, and the delta current is, and so the difference current is the measured, the real fault current minus the predicted current. That will make the relay understand that there is a fault and it will do its stuff. Similarly, voltage and voltage also, predicted voltage and the measured voltage. This is how it operates. This is a very preliminary, what to say, very sketchy idea of how delta algorithms, modern day relays are being based on. Subcycle algorithms are coming into picture because of this feature. Okay, now we have one calculation example. This is actually request was made by some participants. Okay, they wanted some resistive reach calculations to be shown. So I thought, okay, leave it. Let us have one calculation example, one setting calculation, distance setting calculation example as a part of our presentation, so that it will be better for everybody to understand. So I've taken a little, not complicated, obviously not, a system in our utility, in DVC utility. So we will be calculating the setting of this R1 relay. This is the system SLD. We have a 127 kilometer ACSR quad mousse conductor with these parameters, and the shortest line from the remote bus, I've given the name of the buses also. The shortest line from the remote bus is a 17.3 ACSR quad mousse conductor going to Chandauti, and this is the fault level of Chandauti approximately. And the longest line is that of Goya Maitan. It's around 275.5 kilometer ACSR quad mousse. Again, all are double circuit lines represented by this. The fault level is given like this. Now there are 3 ICTs at Goya. Presently there are 4 ICTs. but I have calculated it with 3 because this was already existing in my system, so I copied it. But actually it should have been 4. To understand the concept, the 3 or 4 doesn't matter. With a 14% impedance, this is the connection of 400 kV Goya to 765 kV Goya. This is the connection of 400 kV Goya to 220 kV Goya. Same substation, this is a 2 into 500 MVA, 11.6% ICT. Two ICTs are there, 500 MVA. Here also there is a 315 MVA ICT that has been added, I think, later on or something. On the backward side, I mean, on the local end, we have a line to Bihar Sharif power grid, 111 kilometer quad moves. We have a twin moves conductor line to one of our own power stations, 100 kilometer. We have a 220 kV system of this KTPS unit, KTPS bus, which has a 2 into 315 MVA, 11.6% ICT. Okay, now what is the first thing that we need to do? This is the line length and the parameters. So what we do is, in order to calculate the settings, so this one I am going fast because I will concentrate on the critical parts, not routine work. So I have the conductor data, I multiply it by my conductor length and get my Z1, Z0 and Z mutual. And the remote bus also like this, I get Z1, Z0. Now what I do is I convert this Z1 in terms of my line length. That will be of a help to me, as will be understood later. This 4.36, this is not important. This is not something mandatory. Important thing is this 4.66 at an angle 86.67 degrees. But if you do this, it will help you visualize the thing faster. That is why I personally do it in this method. All the impedances, I convert all the necessary impedances where I have checkpoints in terms of my line length. Matlab, this 4.36 divided by 31.91. Forget this angle. It might have been a twin conductor. With this angle, just this magnitude will do. This is just for our use, not for the relay. Relay will understand these parameters only. So remote bus longest line, this comes to 216.93% of our line length. Reverse shortest line, this will be important because our zone 4 should not go beyond 50% of this. That is the check we'll see. So this is a reverse shortest line, 106% of line length. The principle is same over here. We have the remote and local bus transformer data. So transformer data also, we have 3 ICTs at 1500 MVA, so percentage at 14%. So in the Z base, 14% will be this ohms per ICT. 3 transformers, this will be 3 transformers in parallel. So the impedance, in parallel impedance of all the ICTs will be per ICT divided by 3, and this in terms of line length will give you 15.59% of line length. Mark this word without impede. It's very vital. Impede will be very, very important in this particular setting exam, and in all other settings we'll be doing. The remote bus transformer data set 2. Set 2 is that this one. This is the set 2 I am meaning. This is transformer set 1. This is set 2. So set 2 is this one. So 220 by 400 by 220 ICT is 500 MVA. Similarly, this will come same theory for 58.15% of line length without it. Local bus also we do. We had 2 400 by 220 kV ICTs. So there we do this 92% of line length without impede. And local bus transformer data 2, that will be 2 GTs over here, 15%, but over here we don't have it parallel. GTs are never parallel. So this pi 2 factor will not come over here. They are not in parallel, so that without impede, 40 ohm is the ohmic impedance. is around to 125% something of line length. Okay, now we have a diagram where without infeed all the impedances are given. This is the impedance of this shortest line, longest line. This is the parallel impedance of this transformer and this transformer, this GT, this transformer, all these lines over here. Okay, now we will have a little bit easier to do things. For checks purpose, what is checks I will be covering just now. So nothing as such special about this, very easy, normal mathematics. We have the remote and source impedance. Some relays need it, ABB relays need it to calculate their fault location. Most of the relays actually use it. Remote and source impedance. How is source impedance calculated? You have a 43 kiloampere 3LG fault level, 400 kV bus voltage, unfaulted bus voltage divided by √3 divided by this thing. This fault level at an angle, normally we take 85, 86, even 87 degree, whatever 85 degree is a good approximation of the source impedance angle. So this is a phasor of this magnitude. 5.37 at an angle 85 gives the phasor of this. The complex number will be this. The local and source impedance, KTPS bus 28.5 kiloampere is the fault level, 3LG fault level. So source impedance, this will be local and copy paste error. Okay, local. Now we come to the main thing. This is vital. The impede factor for fault on 765 kV Goya bus. I have. Where is it? Yeah, let me come to this slide first and then go back. How should I tell? When I create a fault in this 765 kV Goya bus, the current will contain the impedes of this line, all these sources will contribute to this, but this current will not be seen by this. So this will increase the impedance of this parallel transformer. It can impedance it to a very high level such that there is no encroachment from here, from this one. The zone 2 or zone 3 will not encroach into this due to impede. So that is what is being checked over here by this impede factor. I create a fault over here, I see the transformer 400 kV this voltage level current, and I see my line current. I divide the transformer current by my line current and keep it as a factor. That will be helpful for me later on. And the factor comes over here 5694 divided by 24 something 2 point something whatever. And this will be useful in doing all this checkpointing. So that impede factor for a fault on 765 kV Goya bus is 2.34. Impede factor for 220 Goya bus is 3 point something more than 3. So this is the lowest. So this is what we need to be careful about. We need to check the encroachment on the 765 Goya bus because the impede factor is also less and the impedance factor is also less. This is the lowest impedance. So all the encroachments will first encroach either on this is the lowest, very low, or on this. So for a fault at 765 kV Goya bus, this relay can operate before any other thing operates. There are other conditions, of course. Second level, this zone 3, what we talked about, it should back up this part, the primary part of this, that one I am talking about. Okay. So these are the two impedances that we have to be very careful about. This 4.35 and 4.98. These are the cases where overreach can occur. Overreach means I have a fault at the lower voltage level, my relay operates from the higher voltage level or a different voltage level, my relay operates at a different voltage level, which should not be the case. This fault should be cleared by its own voltage level first. This relay should never operate for this other voltage level fault. Same for this. And this is a very short line, that is our problem. The zone 2 of this line will encroach into the zone 2 of this line, as will be seen just a little bit later. how do we go about systematically about all these things to be seen? That is being shown one by one. Zone 1 is 80% of line length coming to this value. I'm not explaining further. T1 is 0 millisecond. The timing is 0 millisecond. Without the series compensation, I don't need to increase my time any longer. Zone 2 is 150% of line length because I have mutual inductance, a long line. There's a mutual inductance in the line. So I need to capture my zone 2 faults for the remote bus fault. I have to increase my zone 2 to 150% if I have to capture that. So I told that zone 2 is responsible for tripping of any fault on the remote bus. Beyond remote bus, it is not responsible. It might trip, might not trip, but it should not go beyond the this checkpoints will see. So it comes to 47.88 ohms. Now checkpoint 1, the line length plus 50% of adjacent shortest line. Now we have an adjacent shortest line impedance very low. The adjacent shortest line impedance was 13.67 ohms. Why was it 13.67? I'm just going back once. It was 4.36. Oh, 13.67% of line length. Okay. That is right. Okay. So now here we see the utility of having this 13.67% of line length. What we are doing is we are calculating this one in 150%. Now you can compare on the basis of absolute impedance of 47.88 divided by whatever the absolute impedance is will come over here. That you can do. Otherwise, the method I personally use, this is absolutely personal. I convert my adjacent shortest line into my percentage of line length and then multiply and see all these checkpoints. It gives me a better visual understanding of the problem. See, my adjacent shortest line is 13.67% of my line length, and 50% of that will come 107% of my line length only. Even 80% of the adjacent shortest line will come to 111% of line length only. So if I take a zone 2 average of 150%, my zone 2 is always going to encroach over the 80% encroach into the zone 2 of the adjacent shortest line. So I will have to increase my zone 2 timing. I will have to coordinate my zone 2 timing with the zone 2 timing of the adjacent shortest line. That is why I increase the zone 2 timing as adjacent shortest line zone 2 as 350 milliseconds plus 150 equal to 500 milliseconds. Okay, this is the conclusion part. Now what are all these things? Check 3, 4, 5, 6. This is the transformer one I am seeing. The transformer one without impede we need to see, with impede also we need to see. In the zone 2 case, without impede is the recommended practice. If impede is very high, then you can see with impede. But in impede, you need to use the n-1 contingency. The strongest impede see without the strongest source in service when you see it with impede. Now, if I can, okay, now where from this 15.6 is coming, the via that 765 kV that path transformer impedance, parallel impedance was 15.6% of my line impedance. That is why, so line length plus 60% of transformer, that is coming to 109.36. So it is encroaching, it is less than my zone 2. Even 90% transformer is encroaching, 114%, it is encroaching. Note G, normally checkpoint 4 should not be violated for zone 2 reach. If violated, then 150% may be reduced for phase faults, but for LG reach we need and matlab this 150% can be reduced, let's say 120 we do, but for and the LG reach increment can be made up by using higher K0 values. That is a method. If I have a chance to take a class on only mutual compensation, those things, mutual effects in a transmission line, then we'll see what this line actually means. I increase the K0, increase my to increase the LG fault coverage, where this problem will come, where this mutual effect will be prominent, is 150% is needed. But for the face-to-face fault, I reduce it from 150% to somewhere below to 120% maybe, so that this checkpoint 4 is not violated. But again, nothing is fixed in this world. Now, in this particular example only, we did not reduce it below 150% because the other end is Goya, that is a power grid line. They have all their protections in place, so we can take the risk that. Let me go back. We can take the risk that for a fault at 765 kV, this zone 2 will never operate. They have enough protection in this particular zone. None of the part is not covered. ऐसा नहीं है कि कोई part cover नहीं है. They are not like the other utilities probably, including mine, where a lot of maloperations take place. I'm not blaming anybody. I'm not putting down anybody. But since that is a power grid substation, we are taking the risk that okay, let my zone 2 encroach. I don't have any problems. And this substation has been commissioned for, let's say, 10 years from now. We never had a zone 2 operation or a higher zone, 765 kV fault. Their protection have always tripped in zone 1 or differential or buck differential or whatever. So the history of this is also important in deciding whether we are going to reduce our zone 2 or we are going to take the risk of let it encroach. Let us carry on with it. Checkpoints 5 and 6 are the encroachment with infeed. With infeed, we have not used n-1 over here because even without using n-1, this fellow is encroaching. 90% of the transformer also is encroaching. The reason is that this 3 into 1500 MVA, this impedance is very low. It's a very high transformer, very low transformer impedance is over here because there's a very high transformer MVA involved over here. In majority of scenarios, we do not find so high transformer involved. So this is a very typical problem. That is why I took this case study as a lesson to discuss the various things. Okay, so it's a very typical one. We trust that this voltage level problem will not cause this relay to overtrip for any circumstances. So anyway, in a generality, the checkpoint 4 should not be bypassed. Checkpoint 4 is the limit of zone 2. We should not go. Normally checkpoint 3 also should be the limit, but anyway, you can go up to checkpoint 4. But impede should be taken at the zone 3 level, not at the zone 2 level. Zone 2 timing is much lesser. Okay, so this is about zone 2. Now about zone 3 also similar thing. 120% of line length plus adjacent longest line. So therein we get 380% of line length is the Goya, this line, Goya-Maithan line is so long that the zone 3 of this line is encroaching very high, 380. And all these transformers with this infeed are only taking me up to 132%, including with the full infeed without the n-1 criteria. Okay, for I just want to tell about this n-, what am I talking about is n-1 criteria. N-1 criteria over here means you take, suppose this is a, suppose we take, let's say this line is the highest fault contributor. On doing this short circuit study, I find this line is being the highest fault contributor. I take this line out of service. What will happen? The contribution of this current will increase and this current will remain almost the same. The ratio of this current by this current will be lower. So the increment of this impedance due to infeed will be lower. That is why this is the criteria. Take out the strongest source out of service and then check on the infeed. Because it might happen that I see with infeed my transformer impedance is not encroaching, but one particular day that strongest source is out and suddenly with infeed my transformer impedances are encroached. So better check with the medium possible scenario, not the worst possible scenario. If we really take the worst possible scenario, then half of India will be encroached. So you cannot do settings for point kV long lines. Most of the lines are quite long, followed by quite long lines. So zone 3 will be very high. Okay, so this is checkpoint 1, checkpoint 2. In zone 3, we use infeed to do our things, stuff. Checkpoint 3 and 4 for other voltage level, TR2, that 2 group, other voltage level we will see. We need not check over here because over here this Goya ICT was the 760, so 400 by 765 kV ICT was causing the lowest amount of impedance. So T4 was not checked. Now this 5, checkpoint 5 is important. Zone 3 is supposed to cover the whole bus, the whole longest line. Again go back. Zone 3 of this line is supposed to cover this. We are supposed to see whether creating a fault on this, what is the impedance seen by this relay. We are supposed to see. Normally we don't see. We just blindly give 120% of this plus longest line and hope that it will see. But normally it will not happen. The same impede which is increasing the impedance of this and protecting your relay from overreaching into other voltage, that same infeed is going to create underreach for this relay and this relay will not be able to trip in zone 3 for this longest line remote bus fault. That one also you need to check. That preferably it is operating for line length plus adjacent longest line with infeed. Check the impedance. In this particular case, it will be impossible to operate because if we reduce the zone, we have already taken 380. So this check was not done because already our zone 3 was encroaching into our 765 kV voltage level. So we will not increase this further. This is the down part of it. This is where we decrease the zone 3. This is where we increase the zone 3. If it is not satisfied, we need to increase zone 3. All these 4 checkpoints are where we need to decrease zone 3. This checkpoint already we are burdened with such a high zone 3. So we will not increase any further. But if encroachment is not a major issue, then zone 3 increment. If encroachment is a major issue, further zone 3 reach encroachment is not advisable. Conclusion. Considering infeed for a fault on 765 kV Goya bus, zone 3 at KTPS and encroaches in terms of reach. So time 3, zone 3 timer needs to be coordinated with ICT, HB overcurrent and hard fault protection and kept at 1.04. Preferably, we should have got the Goya end data, overcurrent and hard fault, whatever they have set over there, and coordinate T3 with that. But generally, so much pain is not taken. So it goes on like this. We have a thumb rule and we go on with it. Okay, so this is about zone 3. Zone 4 is 20% of longest line we take. The checkpoint is that zone 4 should not reach beyond 50% of reverse shortest line. Again, go back to the diagram because without diagram we cannot understand. This one, zone 4 of this one should not go beyond zone 1 of, should not encroach beyond zone 1 of this relay. This is the reverse shortest line. If such a thing happens, this relay zone 2 and this relay zone 4. Suppose this relay zone 2 is 500 milliseconds and this relay zone 4 is 500 milliseconds. This relay encroaches into zone 1 beyond zone 1 of this line. So there's a fault on this bus maybe. This relay zone 1 does not operate. Zone 2 over here and zone 4 over here operates at the same time, and we have a false tripping of this line. So that is why the checkpoint for zone 4 is less than 50% of reverse shortest line. And again, like the previous one, less than 60% of local transformer without input. I am not explaining it any further because I've explained transformer impedes enough. Had carrier blocking scheme been used, then zone 4 had to be greater than remote and zone 2 minus longest line. This one was explained in the earlier session. The T4 we keep 500 milliseconds. If local bus bar protection is not present, then T4, the time for the zone 4 timer, can be reduced up to 200 milliseconds for to make the zone 4 act as a bus bar protection. Residual compensation factor and mutual compensation factor, you have to set K0 in the relay and Km in the relay. The equations are as follows, and you it's a phasor, it's a mathematics. This is a complete diagram with infeed. See, zone 2 is overreaching this Chandavati bus, so the timer 2 is increased. Zone 3 is overreaching, zone 3 is encroaching into Goya bus, Goya other voltage level bus, so that timer T3 has also been increased over here. Now we come to load encroachment setting. We assume the minimum system voltage to be 90% at 360 kV. The minimum, sorry, the maximum, no, the minimum conductor carrying capability. Sorry, this would be maximum. That function will be minimum, but what we are doing is we are taking how much current my line will be able to carry. That is the conductor thermal limit, 1.120% of CT limit, any equipment rating that we take, and we find in this particular case the isolator was the weakest point. Isolator was rated at 2000 ampere. The conductor was more or less 2000 quad moves, 600 into 4. Conductor was rated at written over here. What is, how do you see this? 2600 ampere more or less the conductor would have taken, but isolator can only take 2000 ampere. The breaker was much higher, so 2000 ampere has been taken as the line limit. Continuous, the line can handle 2000 ampere. The ampacity of the line at ambient temperature 45 degree and considering temperature rise to 75 degree is 628 ampere as per. If you don't have any other data given by the manufacturer, follow the CEA manual on transmission planning criteria released in January 2013. This has more or less काम चलाने के लिए it's okay. It gives the criteria quite good in very detailed manner they have given. So for a ACSR quad moves, more or less if we take the ambient as 45 as our temperature rise limit as 75, we have to restrict our current to 628 ampere, which comes for a quad move 4 into 630, somewhere around 2500. So we took a minimum power factor of 0.9, which is approximately more than sufficient. In a 400 kV scenario, the power factor will never go below 0.95. The lower voltage levels, okay, in the distribution voltage level, this can be quite less. This can be 0.8 also. In the medium level, 0.9, 0.85 would be okay. What is the minimum load resistance? System voltage minimum into the power factor divided by √3 divided by maximum current. It comes to something 93.53. So the load encroachment resistance will be taken as 90 ohms and the load encroachment angle will be taken as 25 degree, which is the final setting for load encroachment. Okay. Now we come to resistive reaches. Resistive reaches. We have this calculation. I think I showed this one previously also. We have the air resistance phase-to-phase loop calculation. Matlab, this is the base on which we will use the impede factor. The base will be based on what is the base arc resistance we have to consider. We cannot go below it. That is given by this Warrington formula and the minimum fault current. Generally, conductor face-to-face conductor distance is taken, and the minimum fault current we assume it on a very lower range, so that I get a quite a high arc resistance. 1000 ampere fault current at a 400 kV level is too low. We should have taken it more. But anyway, there might be 3 faults and those sort of faults where the fault current is really less. So that is why it has been assumed. Assume lower values to get this arc resistance on the higher side. Okay, so bare resistance for face-to-face loop will be the arc resistance. This is the minimum resistance which has to be considered. And the base resistance for face-to-earth loop will be the arc resistance and the tower footing resistance. Approximately in our system, we take as 10 ohm as the tower footing resistance. Although 400 kV towers have a tower footing resistance of motamoti 5 ohm would be okay. But still we take 4. Let us be on a little higher side. God knows, you have a rocky soil somewhere, the footing resistance is not that good. So better be on the higher side. Now what do we mean by impede factors? Now, impede factor, I shared this impede factor in the previous video. What we actually do is at the zone 1 boundary, we check the remote bus fault contribution divided by local bus fault contribution at the zone 1 boundary. Okay, means at the 80% level, and there we find, let us say this is 2 times. It should be more than 2. Usually it is always more than 2, but okay, 2 is okay factor. We have to balance other things also. This balancing is all about the main the main difficulty in setting calculation is about balancing various factors. It's like this doctor. You try to set right pressure, the sugar level goes down. The sugar, you try to set right sugar, some other level goes down. That balancing is what you need to understand and develop by experience. What I will take, and that is why this is a art, not a science. Okay, so at zone 1 boundary, what is the remote bus contribution by my local contribution? That you check. That let us say it is 2. At the zone 2 boundary, so say the 150% that boundary, 150% of line length, we create a fault and see what is my remote bus contribution divided by my local contribution. Again, this will be more than 3 generally. It has to be more than 3. And this is about the zone 3 boundary. You create a fault and see what happens. Matlab, this is at the remote bus of the longest line. Maybe you create a fault and see what is happening. What is the ratio of the fault current from the other end and the fault current at my relay. And this factor you multiplied by your base resistances to get this resistance, to get the resistance coverage which is necessary. Why you are multiplying, I feel you understand, because the fault resistance is going to get multiplied by this remote bus impede, but the relay is not going to see that. So I need to expand my resistive reach. If I keep only 15, my relay will not really operate if the remote bus contributes equal amount of current and the real fault resistance really 50. I have to create 30 for it. At my in my relay, I have to give 30 ohm coverage. Then only I'll be able to cover a resistance fault of 15 ohms face to face. Okay, that is why this is coming. I hope I am clear. And RSTE is again that impede factors multiplied by the base ones. So 50, 75, 100, might be more. This might be 2, 4, 5, maybe this can go up to 125, 150 also it can go. If you have load encroachment, you don't need to worry about resistive reach coverage. You can go on the higher side, nothing else will happen. The only thing that dictates is the X by R, sorry, this will be R by X, okay. No, I'm used to writing X by R, so mistakenly written X by R. I'll correct it before sending the presentation. So if the resistive reach is too high, then you will have the tilt angle problem. The fault point will move downwards or upwards. That is the problem which we can have with higher resistive reaches. Otherwise, everything is good about it. If you have a 5-degree tilt angle and use higher resistive reaches, that is the best way to solve many problems at the same time. Okay, now there are two other methods also. You can use the fixed RSPP and RSP based on load impedance. If you do that, take 60% of minimum load impedance as RSP. What I mean is, all zone 1, zone 2, zone 3, all will have fixed resistive reach coverage. This is also not a bad proposition. This is also good because I am not really concerned about, let me have a higher coverage. What is the problem? Unless my load is suffering, my transmission line trips on emergency loading, I have no problem. Only thing is that if I have a shorter version of line, then this one, if I increase very much, my fault point may come down and a zone 2 fault may come in zone 1. That is the only disadvantage of this theory. And my RSP I keep as 80% of minimum load resistance. Why this is 60%? Because load will come in RSPP. Load will not come in RSP. Shipping by load will happen due in a phase-to-phase 21P function, not the 21G function. That is why RFP, the phase to earth coverage, can be kept 80%. It can be kept a bit higher also. Nothing will happen. So in this particular scenario, 0.8 into this will be some 74. Let's say 75 and 55. And suppose you have a very short line, not that much long line. You cannot increase the resistance coverage to a very high value. You will have to keep it based on the minimum required. This is must. You should not go below this one. Such lower minimum values may be needed to be taken when lines have shorter lengths, which takes R by X ratio of zones to have values higher than manufacturer recommendations. Generally, manufacturer recommends that for a phase-to-phase, take R by X as less than 3. Do not, if your X value is 10 ohm, your R value should not go beyond 30 ohm. And for a phase to earth, it is around 4.5. If your X value is 10, your phase to earth resistive coverage should not go beyond 45 ohm. But this is okay. This is, this is not, if it is not written in the relay manual, you need not follow directly, but generally we find problems if we increase this thing indiscriminately. The fault point do not follow the straight path. It follows a curve sort of a thing, and that is why you might have a little problem. So in between all this, the progressive is the best, which is shown by this diagram. You have zone 1 a little bit lesser coverage, zone 2 more coverage, zone 3 more coverage. Other things I have already talked about. The same thing, only the starter reaches should encompass, let's say 110% to 125% of zone 3. And generally starter reaches are kept below the power swing boundary. Generally, no hard and fast rule is there, because basically if the fault comes between inside the starter reach, maybe the power swing will be blocked. That is why this thing has been conceived of. But nowadays you don't have problems with these relays. These are very high intelligent relays. This is again all discussed previously. Okay, let me choose this one. This is something which I talked today only, which I talked about today and discussed. There's a 30 kilometer, 4 lines were there. There's a 5 kilometer short line, long line followed by a short line. So this zone 2 was 150% at 45 kilometers. This zone 2 was at, let's say, this is also, let's say, 150%, whatever. What happened for a fault on bus A? All relays tripped. These these two, because this was a zone 2 fault for this, it's a bus fault. This bus bar did not operate or whatever happened, all the 6 relays tripped from here. So this is why this thing had to be 300 millisecond and this thing had to be 500 millisecond. Then only this will, or 450 at least, then only this thing will work. So the remedy also I said over here, you can just read. This is one example. Where this overlapping is taking place and is a cause of problem. I think it is self-explanatory. Nothing more needs to be explained over here. The diagram explains everything almost. Oh, the main thing. The thing happened because there was some work going on. And what happened? This bus section isolator was open, and the majority of the fault current contributor, which would have led to increment of this impedance, so that this relay doesn't operate or this relay doesn't operate, that did not happen that day. All 3 ICTs were on the other side of bus for load management. Something was going on, some shutdown on some PT, something was going on. I've forgotten exactly. But the main thing is this would have covered. Normally, every time this doesn't happen. But on that particular day, this was open, this fault level was not available to save this thing, to multiply this impedance so that these relays do not see this fault in zone. This is one case study I have seen.